Estimating values of the definite integral. Example 2. Values for a function f of t are given in the table below. Estimate the definite integral from 10 to 20 of f of t dt. So we're estimating the area under the curve. And the part that's really important here are the bounds. I want you to notice here that we're estimating what's happening between 10 and 20. So that's not the entire table. That's just the right-hand end of the table. So we have to be a little bit careful about that. You always want to make sure you look at your bounds and know what you're looking for. So now, since we know we're looking between 10 and 20 and we're estimating from a table, we're going to go back to our left-hand and our right-hand estimates. So for our left-hand estimate, our delta t here is going to be equal to 5 because we're counting by 5s. So from 10 to 15, that's 5 units. We're going to pick the rate on the left, which is 42. So we have 42 times 5 plus time 15 to time 20. That's another 5 units. We pick the rate on the right, which is 51. 51 times 5. We add those up, and we're going to get 465. Now for a right-hand estimate, we're going to do the same thing, only now we're going to be picking the rate on the right. So from 10 to 15, if we pick the rate on the right, that's 51 times 5, plus 15 to 20, we pick the rate on the right, which is 60 times 5. We add those up, and we get 555. So our best estimate is going to be to average those together. And so when we average those together, we get 510. So here, our best estimate for the integral from 10 to 20 of f of t dt is going to be 510. So again, if you're using the integral to talk about estimating from a table, you really need to pay close attention to the bounds on the integral because that's going to tell you where you are looking. Let's look at another example. Example 3. The graph of f of t is given below. Use n equals 1 to determine bounds for the integral from 1 to 3 of f of t dt. So what does this all mean? N equals 1 means that we're using one rectangle to approximate the area. And if we're determining bounds, that means we're looking for the over and under estimate because that's what's going to give us the bounds for where the exact area under the curve live. So if we're looking between 1 and 3, let's go ahead and find that on our graph. So 1 is here and 3 is here. So when we have 1, we hit the function up by 2, and when we have 3, we hit the function close to 1. So when we do a left and a right hand approximation, we're either using the left point of the 2, which would be 1, and when we do a right hand approximation, we use the right point, which is 3. So I'm actually going to do a right hand estimation first because I think it'll be easier to see the second one added on if I do it that way. So a right hand estimation means that I'm going to use the right hand point of the 2, which is 3, to help me get my height of the rectangle. So the right hand tip of this rectangle will touch, and I want to find the area of that rectangle. So the width is 2 units and the height is 1 unit. So 2 times 1 gives me a right hand estimate of 2. Now my left hand estimate, I'm going to do the same thing, only now I'm going to use the left point of the 2, which was at 1, between 1 and 3. And I'm going to use that to go up and hit my function. So my left-hand estimate is the estimate I get from when the left-hand corner of the rectangle would touch the function. And so again, I have a base of 2 units because it's going from 1 to 3, but now I have a height of 2 units, and 2 times 2 is 4. So my overestimate is 4, and my underestimate is 2. So those are my bounds. My exact area under the curve has to be between 2 and 4. So that's how I can use n equals 1 to get a sense of the bounds for where my exact area needs to live. Again, I'm paying particular attention to the numbers that are on the bounds of my integral because that tells me for what independent values I need to look between. Now, We want to practice plugging some things into the calculator so we can get really good at computing definite integrals. So let's go ahead and take a look at some examples and make sure we can plug things in to find the area under the curve. Example 4. Use your calculator to compute the following definite integrals. So we have 3 definite integrals here, and we want to practice plugging these in to make sure that we can get the area under the curve using the right syntax. In the main Blackboard folder, under Chapter 5, there's some links to some YouTube videos for various TI calculators that will instruct you on how to calculate the definite integral. You can also Google it, or if you have your manual, you can look that up as well. So, use your calculator to compute the following definite integrals. The first one is the integral from 1 to 3 of sine x dx. So when you plug that all in, you get 1.5303. And what does this mean? What's really important is that we always remember what we're computing. So here, that is the area under the sine function from 1 to 3. And that would tell us that if sine was the derivative of some original function, that the original function would have changed by 1.5303 between 1 and 3. And it would change in the positive direction because this number is positive. Okay, let's try another one. Part B, the integral from 1 to 3 of e to the x plus 3 dx. So when you plug that in, you should get 348.83. Now, when you plug it in, make sure that your x plus 3 is all in parentheses and all up in the power of e. Again, what this means is that the area under this function, which is graphed here, the area underneath that from 1 to 3 is 348.83. That's the exact area under the curve. One last computational one. We have the integral from 2 to 4 of natural log of x dx. That's going to give us 2.1589. So again, that's going to represent the area under the curve of the natural log of x from 2 to 4. I want to talk for a minute about the natural log of x. We have to remember that the natural log of x is not defined for 0 or negative numbers, which means that it would not make sense to have an integral that included 0 or negative numbers. So if you were to try to do something like the integral from -1 to 5 of the natural log of x, you would get an error because the natural log of x is not defined for -1. So your bounds have to reflect something that's actually in the domain of the function. So keep that in mind when you're setting up your definite integrals. Let's look at a word problem example. Example 5. It's important for pharmaceutical companies to test the characteristics of the drugs they design. The strength of the drug is given by R of M, where M measures the dosage or the amount of medicine absorbed in the blood. Suppose an experimental drug changes a patient's temperature at the rate of R of M equals 3m squared over m cubed plus 1 degrees per milligram of the drug. Find the total change in temperature resulting from the first 4 milligrams of the drug. So here, again, this is the rate that we're given, and it's the rate at which the temperature is changing. So if we want to understand how much the temperature changed for the first 4 milligrams, that means we need to integrate this rate to find the definite integral of the area under this function from 0 to 4. So we're going to integrate 0 to 4, 3m squared over m cubed plus 1 dm. So this operator that comes at the end, the variable needs to match the variable you're using because, again, that operator tells you what the variable is. So since it's m here, we're going to put dm at the end. So we're going to put this all into the calculator, and we're going to crunch this number, and we're going to get 4.17. So what does that tell us? So remember, we're finding the total change in temperature. So that 4.17 is going to be in degrees. So this drug is going to change this patient's temperature by 4.17 degrees for the first 4 milligrams of this drug. So that's how we talk about this answer. We have to remember what it represents and how it pertains to this rate. But again, because we have this rate, we are able to talk about the original function, which is temperature, by finding the area under the curve. Let's look at one more problem where we can apply this idea of definite integrals to some word problems and real-life situations. Example 6. The greenhouse effect is the rise in temperature that the Earth experiences because certain gases prevent heat from escaping the atmosphere. According to one study, the temperature is rising at a rate of 0.014 T to the 0.4 degrees Fahrenheit per year, where T is the number of years since the year 2000. Given that the average surface temperature of the Earth was 57.8 degrees Fahrenheit in 2000, let's use that to predict the average temperature in 2200, 2300, and 2400. So again, what we're given is the rate at which the temperature is changing. So if we were to integrate that rate, that would tell us the total change in temperature between 2 points. So for part A, the values we're interested in, T is the number of years since the year 2000. So we want to know how much it's changed from 2000 to 2200, so over 200 years, because again, our initial measurement here is what's going on in the year 2000. So if we integrate our rate from 0 to 200, and we're going to use dt here because our variable here is t, we can plug this into our calculator and we're going to get 16.65. So remember, this is in degrees Fahrenheit, which means that the temperature changed by 16.65 degrees. So if we want to know the actual temperature in 2200, we would add that to our starting point. So if we add 16.65 to 57.8, we get 74.45. So the predicted average temperature for the year 2200 will now be 74.45 degrees. If we want to do the same thing to predict the temperature in the year 2300, we're now going to change the bounds on our integral to go from 0 to 300, because now time is going from 0 to 300 to reflect going from the year 2000 to 2300. But the rate is going to stay the same. And so when we plug that in, we're going to get 29.37. And again, that's degrees Fahrenheit. So again, we're going to add that to the initial degree that we have from the year 2000. So we add it to 57.8, and we get that the new average temperature is 87.17. And then finally, if we want to know what's happening in 2400, we're going to integrate from 0 to 400. We plug in our rate. And again, we plug that into our calculator, and we're going to get 43.94. So that's how much the temperature has changed. Adding that to 57.8, we get 101.74. So if this model is right, the new predicted average temperature for the surface temperature of Earth in 200 years after 2000 will be 74.45, 300 years after 2000 will be 87.17, and 400 years after the year 2000 will be 101.74. And we can use this because the definite integral allows us to take the rate at which the temperature is changing and use it to make predictions about what could happen in the future.